another useful thing is the expected output, right, in terms of the mean and variance for a given input. So working within the constraints of the system will oscillate around 0. So we want to get, let's say it like this, we want to get output, mean sigma for a given input. So assuming the expected value of x is equal to 0, the mean square of a power spectrum density is the expected value squared. I think we also called that x squared and then a bar over all of that, is equal to the integral from infinity to negative infinity of hj omega squared spectrum forcing omega with respect to omega. So for a constant input s, as we looked at before, the mean squared value so for constant input s, right, that's just going to become the expected value of x squared is equal to s naught integral from negative infinity to infinity hj omega absolute value squared d omega. Right? So if we go ahead and look at this equation, so looking at equation 95, to obtain the square of the expected value, we have to have a solution to this guy here. Right? So we need a solution. And, like a lot of integrals, we can just pull that from a table. Right? So from that, so for example, given the solution, we'll leave it in red, the solution for the integral from negative infinity to infinity of b naught over a naught plus j omega a1 squared d omega is equal to pi b naught squared over a naught a1. Right? So that's a good kind of solution we can have. Again, our b naught and our a naught will end up being terms associated with vibrations. Here they're just kind of put in the standard form. The only other one I care about is the integral from infinity to negative infinity of b naught plus j omega b1 over a naught plus j omega a1 minus omega squared a2 absolute value squared d omega is equal to pi times A naught B1 plus A2 B naught squared over A0, A1, A2. Right, and so you can go ahead and use these to solve for the expected outcome in terms of mean and variance, right?